Welcome back to the flight deck. We've seen how a machine lifts off the ground, but now we have to look at the massive challenge of actually keeping it stable once it's up there. To stay in this perfect hover, the quadcopter has to violently shove massive amounts of air molecules downward. Because the blades are moving so fast, the air pushes back, providing the lift needed to stay airborne. Imagine we designed a drone where all the motors were identical, all spinning in the same clockwise direction. It's a layout that looks perfectly logical on a blueprint, but if you built a drone this way, it would fail the moment it left the launch pad. As soon as it gains altitude, the entire body of the drone would begin to spin rapidly in the opposite direction of its propellers, leading to a total loss of control and a quick crash. This happens because of a universal rule of motion. Every time you push on something, it pushes right back at you with the exact same amount of force. When the motor applies force to spin a heavy propeller clockwise, the resistance of the air pushes back on the motor in the opposite direction. This creates an invisible twisting force that will spin the entire aircraft unless we find a way to trap and cancel out that energy. We call this rule Sir Isaac Newton's third law of motion. To feel this invisible pushback for yourself, you don't even need to leave the ground. Find a standard office swivel chair and sit down. Lift your feet entirely off the floor so you aren't touching anything that might stop you from rotating. Hold your arms straight out and then forcefully swing them both together to the right. Even though you aren't touching the floor, the chair will instantly whip your body to the left. That reactive twisting force you just felt is called torque. Your arms are acting like the drone's propellers. Swinging their mass one way forces your base to spin the other way. This is the same problem the drone faces. Every time those motors spin their propellers, they generate torque that tries to spin the drone's body. Solving this requires a specific look at exactly how those motors are placed on the carbon fiber frame. Engineers arrange the motors into a diagonal matrix. Two motors, sitting on a diagonal axis from each other, are wired to spin clockwise. The other two motors sit on the opposite diagonal, and they are wired to spin the other way, counterclockwise. This diagonal setup is key. Because the motors are paired across the center of the craft, the clockwise twist from one pair is perfectly balanced and canceled out by the counterclockwise twist of the other. Since these opposing forces are balanced symmetrically around the center, the total torque is zero. This keeps the nose pointed straight ahead and the drone locked in a stable hover. If we need this perfect balance just to stay still, how do we ever move the drone to look left or right? When you rotate the nose of the drone to point in a new direction while staying perfectly level, you are performing a maneuver called yaw. To yaw, the drone intentionally breaks its own balance. It does this by speeding up one diagonal pair of motors while slowing down the other pair. The total upward push stays the same, so the drone doesn't change altitude. But now the twisting forces are no longer equal. This calculated imbalance allows the drone to pivot smoothly in the air, turning its nose wherever the pilot commands. Our main takeaway today is that managing this diagonal torque is what makes both aerial stability and steering possible. It's a high-speed balancing act. These motor adjustments have to happen thousands of times every second just to keep the drone from falling out of the sky. This raises a question. How is this little computer board in the middle fast enough to make all these calculations without a human pilot even noticing? Understanding these physical mechanics gives us the framework we need to move forward. In our next session, we'll move from the skeleton to the robot's silicon brain.